Good afternoon. Welcome to the 47th ASE seminar, Advanced Supercomputing. My name is Ken. First of all, I'd like to introduce you the brief history of this seminar. So this seminar was initiated by former colleague, he's now in Nagoya. So it started 16 years ago, March 2008. So this seminar is held irregularly when we have domestic or international visitors to the information center. And the other speakers are not necessarily limited to the faculty member of the, our center. And the official language is not fixed, but it's English today. And as I mentioned, first seminar was March 3rd, 2008. And any topics related to HPG and supercomputing. And the last meeting for COVID-19 was 40th, February 4th, 2020. And we have no meetings after that for 3 years. And the online 41 meeting was February 4th, 2022. And the first hybrid seminar was 42nd of April 11th, 2023, last year. So today is the 7th ASE seminar. Today's topic is the programming environment performance evaluation. And our guest speaker is Dr. Teranichi. So he's a group leader and a senior scientist of the programming systems of National Laboratory. So I believe, so this is his third appearance. First one was 10 years ago. Next one is 6 years ago. And in both cases, he was in Sandia National Laboratory. Okay, so before going to the his talk, I'd like to briefly. So Keita received his PhD degree from Penn State very years ago. And after that, he worked for Gray and Sandia. And so after 2022, I believe, so his position. I have known him more than 25 years. So I believe we met for the first time in 1998. Supercomputing 98 at Orlando, Florida. So at that time, he was a student here from the University of California. Okay, so his research is interest about a wide range of the expertise, and I believe he started research career at the research as numerical linear algebra. But he extended his research area to the system software, including the fault tolerance. Okay? And recently, the expertise so focusing on the programming models, performance optimization. And so he's so deeply involved with many DOE projects. And so he is now the principal investigator of the Programming System Sustainability Project, which is funded by DOE ASCL Software Sustainability Seeding Collaborations by post-exascale. Okay, so this is a program today. After his talk, we have 2 talks by my colleagues, Dr. Okay, so let's start. So Keita's talk. Title of his talk is
actually changing today.
Yeah.
Same thing. It is Julia, but I'm trying to cover a broader area of talk.
Okay, so please share the slide.
Again, just a moment. All right. Uh, Good afternoon. My name is Keita Teranishi. Thank you for Kengo. Thank you for introducing me. So I'm a group leader of programming systems of Oak Ridge National Laboratory, which is under Advanced Computing System Research Section, Computer Science and Mathematics Division over there. So this work has been collaboration with lots of members in our section: William Godoy, Pedro Valero-Laja, and Hetman Card, and also Jeffrey Beta, who is the section head of our section. And originally, I was trying to talk about JACC, which is Julia for Accelerator, but I really want to cover broader topics of activities with Julia in Oak Ridge National Laboratory. Today, we have more than 100 users of Julia across the entire organization, not only computer science or computational science and engineering, but we also have some users for people working on neutron facility or other scientific facilities, because Julia is a very easy to use and very powerful language. So we are trying to discuss recent activities in Oak Ridge. So there's today's contents. So I just want to introduce what Julia is. Then I'm going to give you some details of our efforts of Julia for high performance computing systems. Then I'm going to talk about a little bit about our activities, Julia for accelerators called JACC. That sounds familiar to lots of people here, I guess. And we are trying to give some ideas of other activities here. So I'm going to start with Julia's value proposition. Why Julia is important? Why Julia is so great for Oak Ridge, or even broader scientific computing community? So I think so recently, I think for the last 10 years, the landscape of programming language, landscape of computing programming language has been changed. It used to be Tower of Babel. Basically, we broke the, we tried to construct Tower of Babel, but it was not successful for the past years. But so now, considering scientific software, we have C, C++, Fortran, which is people think it is for good performance. But we also have high productivity languages, Python, MATLAB, and R. And also there are so many players. Heterogeneous computing, after we have heterogeneous computing idea, GPUs, accelerators, but we have some like industry or community standard and vendor specific like CUDA, HIP, whatever. And also third party trying to make, language, working commonly for across different platforms. So we are in basically total disarray. However, a major shift, which is introducing the action of LLVM, low-level virtual machine, which is an open source compiler originally developed by people in University of Illinois and by Urbana-Champaign, that provided a common set of compiler framework, like front end, intermediate representation, even common intermediate representation, and also vendor specific backend to translate between intermediate representation to them, machine-specific machine languages, etc. But that actually that changed the total landscape. And if you can, and the others, that changed. But also, there are other things we have to consider. So in high performance computing, we already see slowdown of Moore's law, and basically it is more important to put effort on parallelism, concurrency, and vectorization, and all the architectures, ARM, NVIDIA, AMD, Intel, all these things are doing this direction. And again, having a common compiler platform is really, really useful to develop the software. And also we have a new player, artificial intelligence and machine learning. Also, again, this is also showing the same trend because they want to do some high performance computation, people say tensor, matrix engine, vector, whatever. But most importantly, they are also getting good performance from parallelism. And one interesting trend is if you see high performance computing paper, academic publications, so we see some trend of the use of languages or use of programming framework. Currently, CUDA is more dominant, but as you can see, so that trend changes dramatically. And oftentimes that choice of programming systems is not like a technical, more like a political or other reasons. But bottom line is today's programming systems landscape is completely different. And again, why LLVM is a game changer, I already mentioned it is providing common software infrastructure for different languages, even different hardware platforms. And so basically, bottom line is if you have a programming language, programming source, what we need is just intermediate representation, which is LLVM accommodates. And all basically each vendor, hardware vendor provides a LLVM backend that can translate LLVM IR to their hardware machine language. And so that we can use all these infrastructure to develop your programming systems. I mean, this is, I guess everybody knows this. Intel, ARM, NVIDIA, Apple, AMD, they have their own investment. And if you consider LLVM commits, so the number is, already increasing dramatically. I think today it is kind of, reaching the, plateau, but we already know LLVM is a de facto standard, open source compiler for all these computing systems, also all possible programming system, programming language, programming frameworks. Now, okay. Now we have to rethink what we have to do with computing. So again, we already know scientific computing is pretty hard. And especially in order to write software to flagship computing systems, supercomputing systems. For example, Oak Ridge, we have to write a program for frontier systems, which consists of thousands of nodes of tons of thousands of nodes of AMD GPU systems. It is really, really hard to program, and because previous systems was thousands of nodes of NVIDIA Volta plus IBM Power 9 CPUs. So we always have to change the switching different architecture of nodes, but we have to always adapt. And another interesting observation of scientific computing, scientific application is software is always our specialized scientific equipment. It's not like software product. It's not like commercial software. It's very different from other type of open source software. Basically, software is equipment, instrument. And if you consider more like other, empirical sciences, they often create or build, develop their own instrument to measure something, to recreate certain scientific phenomena, right? And they basically spend, continue to maintain their own equipment, across the generations, of course, across the different generations of students, postdocs, professors, whatever. And I think we are doing such kind of similar activities even for scientific computing software. So then the problem is productivity is always a challenge. And so the problem is if you want to write a program for that runs or that actually allows good portability, performance portability across different computing systems is a huge challenge. I mean, it's hard to expect new students or scientists to always keep up with the latest computing architecture, computing platforms, and aware of these performance features in order to write a program and still doing science. That is extremely hard. I mean, it is basically Hercules. It is a Hercules job. So the question. So then, what we have to think is maybe how we have to maybe lower the barrier of entry. Writing such kind of portable scientific and also performance portable programming for everybody. And another thing is also we have to also consider emerging artificial intelligence and machine learning. They have their own software stack. They have their different culture. So in order to also incorporate this culture, this software stack, is C++, is Fortran good for us? So this is a huge question. And another problem is we have been working on, we have also developed so much software stack under exascale computing project that was ended last year, end of December. Again, software productivity, software integration, and also attracting new users and new scientists is a huge challenge. So that's why we have to come up with different ideas. So maybe we should consider other high productivity or expressive or languages that actually allows scientists to write simple scientific code with ease, and while maintaining good performance and also good portability across different platforms. So that's why we chose Julia. So Julia's value proposition is basically what I said. So if you consider the chart, later kind of the Cartesian domain. So if we consider like fast, slow and easy and hard, what we consider Julia is basically it is easy to program and the performance is great. And also, and another great thing of Julia is a part of LLVM compiler ecosystem. Julia is a programming language that basically there is a front end in the part of LLVM software framework. And also it just does front end takes care of it, Julia language, then basically, LLVM compiler converts to, LLVM intermediate representation. Then vendors provided backend takes care of the program, generating binary and do program execution. And also Julia itself is a unifying workflow language, and also it can be considered as a scripting language because it also provides interactive session like Python or MATLAB. But Julia does not replace Python, but but think about Python's shortcomings. Python actually is one of the preferred language for application workflow, like loosely coupling application. But typically, what we end up with is Fortran code, Python plus other language, or C plus other programming framework, etc. Basically, we ended up with kind of patchwork solution. This is what we don't like. And so I'm putting X. X can be anything like Python, Python, C, Fortran, OpenMP, OpenACC, CUDA, HIP, whatever. And so basically what I want to say, it's nice thing of Julia is okay, using LLVM software ecosystem, and also Julia actually providing unified workflow or software ecosystem, including build system and also library integration, etc. So originally we have this kind of workflow, but we can basically use all the Julia software ecosystem to create workflow more organized manner. And another thing is I also want to say why Python is not good enough. People say Python is mature. Python is a de facto standard for AI and machine learning. However, if you take a look into Python today, Python language extension like Number, PyTorch, or Triton compiler, and also some people are trying to come up with a new programming language called Mojo, which is basically Python or proprietary Python. So the problem is it's not unified. So there are so many choices that also creates a huge confusion to the users. But on the other hand, Julia, maybe users base is small, but their approach of software ecosystem is more coordinated and unified and more controllable from scientific computing users. So this is the reason why we like Julia. And just I want to say Julia's brief walkthrough. So historically, Julia was developed by a team of people in MIT, led by Professor Alan Edelman. And also Julia has two major organization, Julia Hub, it is formerly Julia Computing, and also MIT are major contributors. And the first stable release has been done in 2018. Today we have version 1.10 in 2024. And Julia itself is open source, GitHub hosted packages ecosystem, and the community is growing steadily. And every year there's a convention, JuliaCon, held in July. And this year it was held in Amsterdam, Netherlands, I think. And I think then they are going to have another Julia conference in the next year. So, and nice thing is 95% of Julia packages in the registry had some form with CI. So compared to other software ecosystem, programming systems, programming languages, I think Julia community actually grasped what is going on with the individual Julia plugins, packages, as well as they also understand how they test individual packages. So that also gives big relief for users who want to try different packages of Julia. And let me continue. So Julia is also reproducibility. They are focusing on reproducibility. It is core of their language. And it is also they provide like interactive sessions, Pluto.jl, also Jupyter Network in plugins, and also they provide, as I said, Julia package framework, PKG JL. It is very different from other programming systems. They use AutoConf, CMake. They are very hard to use, or often they are very buggy, but Julia provides very unified, very compressed, concise packaging mechanism, and also they provide a testing environment. Again, it is very unified, very organized software platforms. And also they provide just-in-time or ahead of time compilation with package compiler JL. I think still it is evolving, but that is very useful for future. And another thing is powerful Panda programming for code instrumentation, profiling, time, test set, and LLVM translation. Also, you can also write Julia with native mode, code native. There are lots of meta programming, some, like a language extension to control the details of the program execution. I mean, maybe most users do not need to use these things, but if you really want to write very, very performance, oriented libraries or, routines, you can do this. And also they have good interoperability, C++, Python, and also C. And so that is also strength of Julia. And just I want to show you our recent effort in Oak Ridge. So last year, we tried to create a mini application workflow, and you can get the entire Julia package over there. So what we are trying to do is we are trying to create like a two-dimensional and three-dimensional two-variable diffusion reaction solver, and also it's and plus visualization and also other workflow environment together. So as you can see, so we have even that program is also connected with MPI and also some GPU support, and plus IO package support using HDF5. Julia has a very good interface for that, and also we have some data analysis which is directly connected to Jupyter network, Jupyter network, and we execute entire Julia workflow on Oak Ridge's frontier systems, which is #1 in top 500 supercomputing systems. And this work has been awarded as the best of paper of SC21 of the SC23 workshop. And let me continue. So basically what they are doing, we have done is, so we basically load 7-point stencil, two variable solvers using AMD GPU JL. This is a Julia plugin dedicated for AMD GPUs. And this is a program source on the right-hand side. And the way to write AMD GPU programming is kind of similar to HIP. So basically, if a user needs to know how to program on GPU, but all the language interface is just Julia. And the performance-wise, compared to the bare bone like a LOCAM or HIP implementation, we achieved around half of bare bone HIP implementation. And this is what you can see from from the table. And actually, I put the circle for that. And we can also see the intermediate representation using LLVM, from LLVM. So definitely it is doing good compilation. Still, we are not exactly as fast as HIP version, but we are getting close to the performance compared to the beginning of Julia, or compared to Python. Definitely Julia is much faster. And here is the performance of basically Julia, of our Julia version of application, and we just measured in terms of memory bandwidth. So in the beginning, there's some JIT compilation going on, so that's why it has bandwidth. But after that, code has been optimized, and basically each iteration we basically achieve good memory bandwidth, and actually, that is a good sign. And our Julia-based workflow application has been showing a good scaling up to 4,096 MBA processes, 512 nodes. And in terms of performance variations, so for up to 512 nodes, it is relatively small, but on 512 nodes, but for 4,096 nodes, we had some problems, so due to the libfabric library errors. And in fact, for 4,000 or 8,000 node, we also found some problems with LOCAM, which is a low-level runtime of AMD GPUs that has some issues with the slingshot network of frontier system. But anyway, but bottom line is, unless we don't have any problem with network or low-level libraries, actually Julia is showing a good performance reproducibility. And we also connected Julia with HDF5 and also another special application-oriented file and parallel I/O systems, which is ADIOS2, developed by Oak Ridge. And we have a Julia component of ADIOS2 that also allows basically in data intensive data operations, and the performance itself is pretty good compared to ADIOS without Julia. And for the details, you can find the paper written by William Godoy. And we also did the Jupyter Network tried using Jupyter Network to actually browse the visual image of the output, and everything is done with Julia. So that is also a nice feature of building application and workflow with Julia. And that paper has been actually involved a couple of interns, undergraduate and graduate interns, and they actually, it was also great success. And we are continuing this work to improve more performance and also make it more portable to different platforms. So I just want to move on to other, of course, there are so many activities going on in HPC for Julia, but let me move on to JACC, Julia for accelerators. So the Julia for accelerators is basically a simple idea. We want to provide the same programming interface to different computing platforms. So because currently in major programming, maybe mainstream programming systems for DOE, we have COCOS, Larger, which is a templated C++ programming interface for performance portability. For language extension, we have OpenMP and OpenSEC. So basically the idea is we could do the same thing with Julia. And so that user do not have to use special plugin of Julia for CUDA, Julia for AMD GPU, Julia for SQL, or Intel GPU architecture. So this is what we came up with Julia. So basically writing COCOS-like programming framework for Julia. So if you see COCOS, COCOS is just a lightweight C++ class library that that actually creates an interface to different backend runtime systems and architecture. Basically, we are doing the same thing with Julia. So if you see the diagram on the right, lower right, so we have a Julia applications. Then there's a JACC library call, or program parallelization with JACC. Then JACC basically calls backend corresponding to threads, CUDA version, AMD GPU, one API, or other backend. Then we have a Julia LLVM to take care of all the just-in-time compilation and making some runtime call, runtime systems call, runtime call, or systems call underneath. So very simple ideas. And currently we are having good growth of community, from Lawrence Berkeley National Laboratory, Argonne, MIT, ETH, and also Simon Foundation. And they are also showing some interest of using JACC to write their tensor decomposition libraries. And how is JACC implemented? It is actually very simple Julia-based class, Julia-based function implementation, and JACC also provides very simple content for parallelization and data encapsulation. And basically, we have two major capabilities. Julia JACC array. JACC array is basically data abstraction of memory allocation on the corresponding node architecture, and it is very similar to COCOS view, and which also represents C++ class representation of memory allocation, and for different, also takes care of data layout, data locality for CPU and GPU. We are doing the same thing through JACC array. And now for parallelization, we have JACC parallel for JACC parallel reduce. Basically, it is very similar to using basically taking function as a part of the input for JACC parallel 4, then JACC parallel 4 invokes that function in parallel. Very similar to COCOS parallel 4, or maybe some has some similarity with OpenMP's parallel 4. And we also provide some basic data primitives, JACC1s, JACC0s, and also we are working on JACC shared, which is JACC's representation, Julia representation for shared memory of accelerator devices. And then we are just showing the performance of JACC with very simple 1D like brass-like operations, or and also lattice Boltzmann computation LBM with different GPUs, different CPUs. Basically, we don't see much performance loss compared to Julia's original plugins for different architecture. Basically, very, very thin. And we have already have some publications of Julia workflow, as I said, also JACC. And if you are interested, please let me know. And currently, we are also working on JACC for shared memory, which is basically abstraction for shared memory implementation of through Julia. And we are currently on, this is still ongoing effort, and we have just submitted the paper to one of the workshops, so hopefully this will be accepted. And there are some other ongoing effort in context of JACC. We have JACC Brass, we have JACC Multi, which is multiple device support. And also we are going to put JACC Auto, it is auto tuning. Basically, you can encapsulate the piece of code, or you want to parallelize, you want to improve performance, then JACC Auto actually empirically compiles during runtime, like what we do for just-in-time compilation, then to choose a best kernel implementation. And now, then where we should get to study to learn Julia. So in Oak Ridge, we actually have one of the GitHub repository, and we are putting all example programs, workflow programs, and JACC implementation in the GitHub repository. It is free, it is open to everybody, and open to everybody. So if you are interested, please let me know. And also there are so many materials of Julia. I don't want to spend time to cover every single items, but we have been very active to make Julia more accessible to different research, people in different research domains. And also recently, we also studied the capability of GitHub Copilot or large language models to see how these large language model services, generative AI services, can generate Julia programs, just with a very simple, prompt. And this is one of the study. We just put very simple prompt through GitHub Copilot, say kernel name, function kernel name, something like that, and try to see how much, to understand how much it can do. Good job to generate kernels. And in this case, we just tried 4 different Julia plugin threads. It is CPU thread, CUDA, NVIDIA for NVIDIA, AMD GPU, it is plugin for AMD GPU, and kernel abstraction, it is actually intended for Intel's GPU architecture, basically SQL. And still 0.2, we are putting very, very subjective evaluation to rate its capability. 0.75 means it is doing a good job. 0 means all the generated code are totally useless. And 0.25 it is doing maybe one of the source code out of 10 seems good, but the rest of them are totally useless. 0.5 is a few source code are working, but others are not useful. So it is very subjective. But bottom line is, Julia is still not so popular. I think that's the reason why large language models, generative AI services are not able to generate very correct code. But currently we are working on how, changing, how, our number one, training these large language models to generate scientific computing, like for example, Julia source code. And we are also studying what kind of prompt, basically prompt engineering, or or expression of prompt to make generative AI to generate correct code. And also recently, we are also studying maybe we could create another intermediate representation amenable to large language model. And also lastly, I also want to advertise the project led by me. It is a stewardship for programming systems and tools, which will continue until 2029. I am the PI of the entire project. Basically, it is a post-exascale ECP project, exascale computing project, software stewardship. And so there are 8 national laboratories, a couple of universities, and several collaborators working together to continue the advancement and stewardship of different programming systems. And Julia is one of our portfolio. And because, as I said, Julia is getting more attention, and we also see lots of potentials. And I'm hoping Julia is going to be one of the major language for the post-exascale computing landscape, and plus AI and machine learning integration. And lastly, I just want to acknowledge this work. My work is using part of Oak Ridge's leadership computing facility, and also funded by Department of Energy Office of Science. And there are also, I want to thank my co-author, our co-authors, William Godoy, Pedro Valera, Hetman Card, and Jeff Vetter. And also there are a couple of other sponsors. It is CAS. CAS is a consortium of advancing scientific software. It is a new consortium for post-ECP software sustainability and stewardship. And maybe in this year's supercomputing conference, you will see maybe a few both sessions, panels related to this consortium. And thank you for listening. Any questions?
Okay, thank you very much. So next speaker is for Unity. He will talk about performance portability.
Thank you for the introduction. I'm Yohei Miki from this center. And in my case, my programming method is much lower level from the previous talk. So I will use CUDA, HIP, and SECO. And target devices are NVIDIA and AMD, and also for Intel GPUs. So, okay. So the currently GPU is the most dominant accelerator devices on recent supercomputers. And GPU is essentially a parallel computer. So single GPU has an order of thousands or 10,000s of parallels in single board of GPU. And in these 10 years, majority of GPU supercomputers are basically NVIDIA GPUs. But in recent years, there are some AMD GPU supercomputers like Frontier, and also Intel GPU supercomputer Aurora. So currently, #1 system is AMD GPU. Second system is Intel GPU. And third place system is Eagle accelerated by NVIDIA GPUs. So 3 vendors win the top 3 spots of top 500. And such competition among GPU vendors accelerate the performance improvement of GPUs. So 4 or 5 years ago, so acceleration of GPUs of NVIDIA GPUs is around square root 2 in each generation. For example, P100 to B100. But in this Hopper generation, there are 3 or more acceleration from 100. So that is one benefit of such competition among GPU vendors. And but there are 3 GPU vendors and providing 3 programming models. So we must choose one of them. So such investigation is one of my work. And this is some chart of programming environments for GPU, but basically limited to lower levels, not including Cocos or Julia in here. But so for low level implementation, CUDA is for NVIDIA GPUs, and HIP is basically for AMD GPU, but HIP implemented code can run also on NVIDIA GPU. And in case of SECO, basically this support Intel GPU, but for Intel One API case, we have another plugin provided by CodePlay. By using this plugin, we can run the secret developed code also on NVIDIA GPU and AMD GPU. Also, there are another compiler, so named Adaptive CPP. This compiler supports SECO and also basically supports all GPUs. And also there are many other options, but I will provide this layer only today. And here's some note for constructing the SECO environment by yourself. And easiest one is installing Intel One API, and also for use plugins for NVIDIA or AMD GPUs. Another choice is using Adaptive CPP, and we can install just following the installation guide. And the most important one for Adaptive CPP is we can use on NVIDIA Grasshopper system. So Intel One API is compiled by Intel and supports only x86 CPUs. But the CPU of Grasshopper is NVIDIA Grace. That is ARM CPU, not supported by Intel One API. So, but Adaptive CPP can support Grasshopper. That is one merit of this, another option. Okay, I skip this very detailed comment. And in the chart by Teranish-san, so maybe C++ is categorized as hard or difficult language, but for me, CUDA is very easy. so because I have more than 10 years experience in CUDA, so I can develop from scratch by using CUDA. And when learning the HIP implementation, first one is converting some simple CUDA codes by using HIPify clone. Then we can compare the CUDA implementation and HIP implementation. So we can learn easiest. So now, for me, it is straightforward to write CUDA, write HIP codes from scratch. And in case of SECO, there are another source-to-source translator from CUDA code. And current name is Cyclomatic. Formally, that is DPCT. Maybe data parallel C++ translator or something. And but there are some different features with CUDA. And actually, Fujita-san, they helped me for this tips. And so actually, my recommendation for CUDA developers is using in-order option. So in this case, so the behavior is very similar to NVIDIA GPUs, but the default is not this case. And okay. And the next one is my target application. Actually, I'm an astrophysicist, and my main target is galactic astrophysics. In such field, N-body simulation is a very powerful tool. So I'm developing N-body codes for my study. And in N-body simulation, we calculate time evolution of gravitational many-body system by solving Newton's equation of motion. And this is the most simplest one that, called direct method. And this direct solver is also a backend of tree method. So we can use still in tree method for backend. And also this is employed in collisional n-body simulations, such as systems near the black hole or globular cluster. Okay, this is it. And in my study, I used NVIDIA 800 and Grasshopper, and also AMD MI210, and also Intel GPU Max 1100. And so please keep in mind, so NVIDIA GPUs are basically 3 times higher theoretical peak performance compared to this one. So these GPUs are high-end GPUs in Hopper generation, but these GPUs are not high-end GPU in this generation. And basically the PDP for AMD and Intel GPUs in this study is 300 watt, but NVIDIA GPUs more power. So TDP for NVIDIA 800 is 700 watt. And TDP for Grasshopper, including the CPU and memory, but actually, actual TDP for GPU part would be same with NVIDIA 800. Okay, and first of all, optimization for n-body simulation is calculation of this part, so the inverse of square root. That is the most essential part for optimization. And in case of NVIDIA 800 case, and also for NVIDIA Grasshopper case, if we use CUDA, then the best instruction is R square root F. That is a little bit approximated one, but fast one. And for AMD GPUs, R square root F is not the best option. That is this complicated name instruction, but provides faster or higher performance. And this is IEEE compliant intrinsic. And okay, and for if we use SECO, there's no R square root of FR square root Rn, but we use SECO R square root or SECO native R square root. And in case of Intel compiler, that is highlighted in blue characters, basically same performance on same GPU, except for this case. So actually, so Intel compiler can find the best interaction on each environment. And in case of adaptive CPP, especially on NVIDIA GPUs, is highlighted in brown characters. In this case, the performance is around 8 times 10 to the 11th, but this is very lower than CUDA case. So, and very similar performance to this not optimal instruction. So we must use the best instruction even on NVIDIA case. So we use device-specific features to use the best instruction like this. I skip the details of this, but we have such options to use the best device intrinsic on for adaptive CPP. In other cases, for on AMD GPUs, this adaptive CPP can find the best instruction. And also for Intel GPUs, we test the only for Intel One API, but basically the performance is the same for every instruction. After that, we further optimize the code. For in case of NVIDIA GPUs, we perform the parameter survey to find the best configuration. So, for example, number of threads per block, the most essential one, and also unrolling counts, number of instruction level parallelism, and usage of shared memory, including single or double buffer mode, or per block or per warp synchronization. And also we use, so here the memcopy async is some special instruction. So we can store the data on global memory to shared memory without bypassing the register on the streaming multiprocessor, and also adoption of flash to zero option for subnormal numbers. And we repeated same things for AMD and Intel GPUs. But for AMD GPUs, we have another option. So that is packed FP32 instruction that doubles the performance of fused multiple add and addition and for multiplication. So by using this, basically the performance is doubled, except for reciprocal square root instruction. Others are same for Intel CPUs. And also, we monitored GPU status during the performance measurement. So actually, we monitored temperature and clock frequency and power used by GPU only, not including CPU part or memory or chassis fan. But we can monitor such metrics by using NVMe or ROCm-SMI or Intel Level 0 Sys1 API. Also, we used unused cores for main computation by using OpenMP task. So this monitoring does not interfere the main measurement of the performance. Okay, this is the result of performance measurement. The upper panel shows the performance, and the horizontal axis is the number of particles, and the higher is a meaning better performance. And this panel is for NVIDIA H100, and that's for Grasshopper. In this case, SQL code compiled Intel 1 API is the fastest on NVIDIA GPU. That is a bit surprising result for me. But anyway, this is the result. And also, the second one is CUDA code. And the third one is adaptive CPP. And the fourth one is not my code, but this is a sample code included CUDA samples. So this is a code optimized by NVIDIA. But by my optimization, my CUDA code is much faster. So, okay, for NVIDIA H100, in case of a Grasshopper system, we have no option to use Intel 1 API. So, SQL ICPX result is missing in this panel. But the CUDA and adaptive CPP performance is basically the same on H100 and GH200 because GPU part is actually same. And for AMD GPU and Intel GPU, the theoretical peak performance is 1/3 of in this case, but the achieved performance is around half of these GPUs. And okay, there are 3 kinds of performance curve, and the highest one is HIP or adaptive CPP case with packed FP32 instructions, and the lowest one is HIP or adaptive CPP without packed FP32 instructions. So this gap is an effect of packed FP32 instructions, and the Intel compiler partially uses packed FP32 instructions. That is why there is in between the packed FP32 or without case. And that is a result for Intel PVC. And also, lower panel is energy efficiency on this measurement. Because we monitor the GPU power, we can convert these results in terms of performance per energy. And also, NVIDIA GPU wins this comparison. Basically, the process rule of GPU is the finest in NVIDIA GPU in these generations. Okay. I said all things, so okay. I can skip this slide. And this is a detailed GPU status in the performance during the performance measurement. X-axis is time from the start of simulation, and the top panel is temperature, and the middle one is GPU power, and the lowest one is GPU frequency. And in case of which one? NVIDIA GPUs, the temperature is around, saturated temperature is around 50 degrees or 60 degrees. But this is for SXM form factor case. And for AMD and Intel GPU, we used PCI cards. So cooling function is a little bit lower than SXM. So temperature is a little bit higher. And for the power usage, so NVIDIA GPUs use up more than 600 watts for everybody simulation. And in case of AMD or Intel GPUs, power cap is 300 watts. So that is capped. And for the clock frequency, NVIDIA GPUs achieved the boost clock always, and also for Intel GPU. But in case of AMD GPUs, the clock frequency decrease by using FACT-FP32 instructions. So the lowest one is always, we use always FACT-FP32 instruction case. And the blue one is a partially FACT-FP32 case. And the highest one is nearly boost clock. That is without FACT-FP32 case. And here's a performance projection for high-end GPUs, especially for AMD and Intel GPUs. So in case of NVIDIA, they are high-end GPUs. So there's no estimation. But in case of AMD and Intel GPUs, we estimated their performance by two ways. First one is the ratio of the theoretical peak performance, and that is curves with lower arrows, because this is just an upper limit of estimation. So in case of this estimation, so for example, for AMD MI250X, there is 2.1 performance improvement from MI210, but the total board power is only 1.87x. So power is not sufficient. Even on the MI210, we encountered this behavior. So actual performance will be lower than this curve. And the second estimation is based on the energy efficiency. So basically, we observed performance per energy, and the supplied energy is doubled or 1.87 times. So we can estimate based on the power efficiency. That is this curve, and this curve. In this estimation, these four GPUs shows a very similar performance, but NVIDIA wins in this comparison. Maybe, right. So this is a summary. 時間ってどんぐらいでしたっけ
25分からまあそろそろ。
まあそうそう。Then, okay, I will show one more slide before the summary. So I also compared this best implementation with directive-based GPU floating case. So black one is a secure code or HIP code or something like that. So best one case. And the colored results for OpenSSE or OpenMP case. For NVIDIA GPUs, we can use OpenSSE and OpenMP target for GPU offloading. And red curves are for OpenMP case and blue ones for OpenSSE case. On NVIDIA 800, OpenSSE is better for OpenMP than OpenMP. And that is around 80% of the best implementation. And on AMD GPUs, we have only OpenMP target, but we have two options using loop or distribute directive. The performance for these two options are almost the same, and that is 70% of best implementation, and also similar for Intel GPU. Okay, that's summary of my talk. Thank you for your attention.
Thank you very much.
Thank you for introduction. I'm talking about some hierarchical hybrid center-wide computing using WaitIO. So here's an overview of my talk. So first I talk about some WaitIO video and HC open video, and then go to start the WaitIO overview and its application. And finally, I'm going to talk about some next WaitIO development at JACC quantum project. So let's talk about it. So now we are operating a WaitIO video for simulated data learning. So it's the world's first real heterogeneous computing system. So because our WaitIO consists of two types of clusters. One is Aquarius, this is some GPU, Intel GPU with GPU and A400. And the other one is some Odyssey, it's a commercial version of Fugaku in FF1000. So what is the combining the Odyssey is a simple MPI job over is impossible because it's just two different kind of system. So, but actually, we would say and Aquarius is connected by a 2 terabyte one infinity band and 2 type of shared file system. So here's some we developed the H3 open system WaitIO socket, and also live interpol convention through the NVIDIA NVIDIA. And also we developed some H3 open using MP that is a higher level couple. And also we developed some operating environment. We developed a coupling job schedule because using some combining two systems with Odyssey and Opera, there are two kind of some TCS job management system. But so user needs to submit two jobs. But so we developed a coupling job schedule. That means that we submit two kind of jobs. This is some of the co-scheduled job, some defining some special resource. In this case, there are two jobs. When this is Odyssey part and Aquarius resources available, the coupling job schedule automatically submitted to job. So the coupling is a two kind of schedule. So next year I talk about some HC open video software. So it's an innovating software platform for integration of simulation, data, and learning on the with the video system. There are three innovations. One is the new principle of numerical analysis, adaptive question, automatic tuning, and also accuracy verification. Second part of the hierarchical data-driven approach. It's based on machine learning. And third part of the software utilities for the heterogeneous environment, such as the WaitIO. So we combine three types of integration in the system. But I talk about in this presentation in the third part, in the software utilities for the heterogeneous environment, such as WaitIO. So WaitIO API is very, very simple. It's basically WaitIO ISN, and directly and await. Maybe just the same as the WaitIO MPI ISN directly await. And also some of our miscellaneous functions that combine some making a group of the clusters. This is a three kind of MPI application. So there are three different applications. But using this WaitIO, we can create a group for some each application and combine to some coupling communication to the among the MPI applications. So, but WaitIO API too simple to write a program. So, but we also develop a WaitIO MPI conversion library. But that's a problem because the WaitIO doesn't have an MPI data type. So that is very difficult to translate MPI program to WaitIO. So we develop such kind of thing. And currently, we develop some IC and RSC and reduce because or reduce such kind of thing, these kind of things. So if we just use the request, we implement such kind of corrected information. So here's some of so how MPI application can be maybe convert into the WaitIO. This is some photon program. Is Vertex is the original photon MPI program. But when you use some WaitIO, you can add some red part. Maybe you can see some of this is MPI ICN, but that adding some prefix WaitIO underscore and almost some here is some data types and some operation on all this. It's kind of mechanically compatible. So currently some WaitIO socket is how much performance. Here is the Odyssey part to node because some limitation of the ASE processing power and some limitation of the communication software on the FX1000. It is around some two node application, just only some 300 megabytes per second, but by you made a circuit. So increase the performance we develop in the WaitIO file, but in the communication between some fast file system. So using a file is up to the 1 gigabyte per second. So when I talk about some how we accelerate this performance. So what kind of WaitIO application? So one is some of this coupling operation. So this is a real-time data processing and simulation. We are processing the S plus D square, D plus A. So this is the real-time data processing and simulation. And in this application, 3D earthquake simulation with real-time data processing simulation. In this application, in Japan, there are so many earthquakes. So and some JACC that that's kind of data in real time and in the some real time accuracy, getting the data and some of filtering and send the data to the simulation part and the Odyssey by using some WaitIO and processing some of simulation and go back. And this is a very difficult thing, but usually this kind of application can be write a file write and file read, but we replace such kind of path to the WaitIO socket. So just the accuracy part, data saying the send, that can WaitIO MPI send, and then the receiving part of this is some of the WaitIO MPI I receive. That's only. It's very easy. And second part of the WaitIO and UTMP application. This is a high-level coupling software. So this, in this case, maybe atmosphere machine learning coupling. So in the climate simulation, it is these are the main issues in the high resolution to cloud resolution. However, to maybe high resolution is cloud resolution too much higher cost. So it's difficult to apply to the climate simulation. So it's around 10 years and 100 years. So that how to use that? So we use some high-level resolution simulation data into using machine learning part. Some other parameter using some low resolution data. Let's come out some high resolution using a machine learning. That's the technique. So how to do that? So we use such kind of some Odyssey part in the climate simulation in the Nikon, and in the accuracy part we use machine learning to use this part. So here is some countries, some prototype calculation results by using some web socket and UTMB. And here is some input of some data and some center part of the simulation result and third part of prediction in the machine learning. So the roughly distribution in the barrier with maybe reproduce, but some reproduction, some extreme value is not so good. So we are continuing to approaching about that. So how much performance? So we compare to the some such as the machine learning part and some like simulation part in the OSA, and also the heterogeneous part in the Nikon part running the OSA and machine learning part in the accuracy using GPU. And some orange part is the homogeneous part, and some yellow part in the using heterogeneous. You can see that some around 35% by the accelerated by heterogeneous computing. So WaitIO is applicable so many things. So it's very easy. Some using currently such kind of coupling commission using some shared file, but this kind of application can be used easily to translate to the WaitIO. And second thing is this is a tricky part in the toy program, but you can some of the family. It's the same one split data structure. It's maybe usually some single cluster, but by using WaitIO, some of the part can GPU and some of them can be solved as GPU. That kind of possible. And we are working on the JCPCM project for heterogeneous computing and using JACC. And because of the University of Tokyo, maybe with a business one and also maybe Hierarchical supercomputer and the modular supercomputing architecture, that's the MSA. This is very similar machine architecture, and we are now collaborating in some JCPM projects. And we are maybe treating such a target application in maybe JC and CEA. This is one is a transmitter system modeling platform, TSMP, and JPC, and brain anatomy simulation. And also we are collaborating in the CEA. In this part, maybe we are using some two kind of application. So it's a deep system, JC, and maybe with a video and Tokyo. So we have TSMC and brain anatomy simulation. So two kind that can be done on a deep system and also with a video. So we have some results paper, and that kind of accepted. And so in this September, I presented some workshop with some results. So what's the next with the development of JCB quantum project? So JCB quantum project is a hybrid system quantum computer and supercomputer QC as an accelerator. Maybe a 5-year project started last year. And the project can CCS and we did SoftBank. And we University Tokyo and Osaka will join the project. In this project, we are planning to system software for quantum computing and HPC hybrid environment. And because some system software and some efficient smooth operation is so that's very important. So in this project, we plan to develop some QH schedule. That job schedule can be simultaneous use such kind of multiple centers because in Japan there are so many 400 gigabyte mathematics China. In this project, there are several centers. Some center has some QC and HPC, and some center has QCO. So we are connected such kind of center and realizing heterogeneous computing. And second part of the project is H3 Open VX QH. So this is maybe expanded some H3 Open VX. It's a coupling to efficiency to using some kind of the system, maybe system and system, but this kind of stuff is expanded to the center-wide communication. So in this case, we have two types of development related to WaitIO. One is a WaitIO router. This is a center-wide communication. And this kind of stuff in the center-wide communication, there's two kind of issues. One is the performance. It's a very long distance networks and high latency. And second issue is some of security and part. But my application is not has to be the same thing. And this is such a system of paper. In this case, WaitIO router, in the center, high performance communication using RDMA and zero copy routing. So we developed some WaitIO verbs and WaitIO talk. Instead, maybe WaitIO socket is not so good, but in the WaitIO physical, so we expanded the WaitIO verbs in the directly use the infinite band lower networks and WaitIO talk producer. I had to talk about it. And also, this kind of WaitIO router, that means the zero copy routing. And also among centers, this is some technique to one RDMA communication to expand the multi-stream TCP/IP connection. So you can expand it and increase the bandwidth because the high latency network, if it is some multi-stream communication is effective to increase the buffer. And also for security with encryption and maybe scrum packets and also compression. So you maybe if you use some A center and B center. In the center, we can connect the RDMA and some of the router to some of the Synapse router. In that case, it separates the multi-stream TCP network with encryption and data scrum. And then go to the other centers, it may be directly converting the RDMA to expand network. And here's now structure, maybe, and this kind of stuff. So in this WaitIO support and verbs and TOF and socket and file. Here's performance in the WaitIO verbs in the multi-layer in Aquarius. Because Aquarius has some 4 infinite HDR networks. And here's some TCP/IP connection, and here's some latency of some of the WaitIO socket and verbs. It's almost 10 times, maybe 1/10 of the latency of 1/10. And this is communication bandwidth. This is by using a socket in about 4 GB per second. The one link to HDR is almost 24 GB per second. And WaitIO is in the multiple process per node. In that case, up to 4 stream by using some 96 GB per second using WaitIO. And here's some of WaitIO verbs on the material environment. Actually, different system different infinite if you have any 400. In that case, maybe one link is 47 GB per second, and using some of 4 streams by using 8 processes, it's up to some of 191 GB per second by using some application. And latency will say. And next is some WaitIO talk on Odyssey. Here's one HTTP, maybe 3.4 microsecond. Because this is a WaitIO socket, it's not so fast, but his U12 is directly in the U12. And here's some latency. And bandwidth is completely faster because I said some WaitIO socket performance around 200 megabytes per second. But using some WaitIO U12, I thought them using up to 6.4 gigabytes per second. It's fast. So next thing is WaitIO for pipelines. Maybe Terence talk about some Julia. Maybe I can implement such a WaitIO.j. That can be possible. So because I developed some WaitIO file, because some of many of some quantum computing use a Python-based interface. So we can use some directly connect to the Python. So we prepare some providing WaitIO interface for Python. It's very easy. In that case, maybe there are 4 kind of application. It's 2 kind of application, MPI application, and 2 kind of maybe application use some of Python directly. In that case, we can communicate for each other. Here is adoption Python interface, and it is some of Python is very difficult to some immutable projects. So we can provide such kind of some object. Maybe from the WaitIO to Python data conversion. It's very easy. So, but the communication buffer is using some NumPy array, and my function is C version limited. So it's very easy. But currently we provide such a miscellaneous communication and WaitIO receive and write that only. Using statistical communication, we can combine in some NPI application, CPU cluster, and some Python using some GPU cluster in the machine learning, and also we can provide such kind of interface to quantum computing. And here some result. This sample code is very easy, this kind of stuff, and we can some kind of some sample run is very easy to pinpoint. And here's a Shirag sample, this kind of stuff. And also, we can pinpoint C program and maybe Python. That's only. So we're using some, we can expand some WaitIO stuff to CPU and different CPU, and also different GPU, and also the other quantum communication. So that was my talk. Thank you very much for.
Thank you.
Yeah, thank you very much.
I have to say some closing remarks, but no special word. But well, thank you very much for joining us. Yeah, I would like to thank the speakers, especially Keita, and audience discussions. And we are now more numbers on-site participants than before. So I hope it's getting one more. Yeah. So we are now scheduling several future meetings. I'd like to inform you later. Unfortunately, so Kashiwa is not so convenient place. So everybody comes to this place in the next time. Okay, thank you very much again, and see you next time.